Hello everyone, today we're going to look at the phased LSTM implementation based on our previous implementation of the a little bit jacked up LSTM, vanilla LSTM with the peepholes, so it's not like totally vanilla. It's basically based on the equations from the paper. So if we look at these equations, so on this chart A, that was what we implemented last time, and now we're going to implement B. So here in the B, what we need to be aware of is that, see here there are two places where as an inputs you also get T here. So this is an index T of the time step. So it's like just following from 0 to some maximum sequence length. And also the comment is that some of the state-of-the-art LSTMs, some other models, they actually concatenate T to the X, so that is a common strategy of like improving a little bit the performance of LSTM. So in this case it's not concatenated, but it's directed to the gates K. So those are these phased gates. Last time we implemented these equations from 1 to 5 for the very basic peephole based LSTM, where the peepholes are these ones and the other parts are as a simple LSTM. And yeah, okay, hopefully. So and then here we have the new gates. So with the input comes T index that we pass for every sample, so for every layer. So every layer basically is an LSTM cell. And here we have some learnable parameters. Actually, in some implementations that I have seen, they also try to learn the R parameter. I think also here in the paper somewhere mentioned that you can get reasonable results also if you learn everything. So you have just like a like adaptable structure that you learn things. So the gates itself, they are K gates here, and everything with regards to K gates are based on this parameter that you have on this side, phi. So this one, phi parameter. So this is actually not a parameter, just like like equation that you use, and the parameters are actually the theta, well, not theta, but this tau and s, and the s is shift, basically phase shift. Those are the learnable parameters, tau and s. Then r parameter is a hyperparameter, but it can be also learnable, of course. Then alpha, again, can be learnable or it can be a hyperparameter. And also, so it's a bit like a leaky, like this, so that the gradient doesn't disappear. But there is also somewhere written, I need to quickly find, that the alpha is actually set only in training time. So in the test time it's set as 0. You can later find the place where it's written like that. And the K gates are included like this. So they are in the middle of the cell state and the hidden state. So that's basically the last thing that's there. So they are in the between all of those things. And the problem here that is not mentioned in the paper at all, that is kind of interesting, is that mod is not there is no derivative for mod. At least as far as I know. So you could probably create some rules basically, but in general, so there is another alternative. The alternative that I found in the PyTorch forums. So one guy posted these like functions that you can use as an alternative. So if I like compare this, so the simple mod function, like with the floating point, looks like this. So if I increase the interval, let's say for 2, so if I enter anything like here from this side till 2, so then I will get out the So it increases, and if it matches the interval, then I get out the 0. So that is the proposed effect of the mod. So for example, if I input 4, I will again get out 0. If I input 6, I will get out 0. If I input 2.5, I will not get out 0, but I will get the remainder till the next this place where it goes down. And actually, so this person, I'm not sure if he invented this himself, probably not, but there is the alternative how you can write it with tangents and arctangents. And it basically have the exactly same way how it operates. So yeah, so we'll use that one for the mod. And I also shared that code for you. I think that's about it. We can start working on the code. So if I go back to the, if you have any questions at some point, you can also ask, of course. So I'm also not completely total expert on this, but I at least run some experiments, got it working. So one thing that I also implemented is that I have the input features it can be configurable, because so we have 28 by 28. That is 784. So theoretically, for this MNIST thing, we can have the 784 time steps for each sample, because it's 28 by 28. But we can also reduce the complexity of the task by, for example, entering the input features as 28, and that I actually would advise to do right now, because of course later all benefits of the phased LSTM is with the large sequences, but right now for the testing purposes it's not a good idea to test something with input size of 1, because otherwise some of the equations can work really good with 1 but really bad with something else than 1. So and 28 is also easy, because it's just rows from the image, and that's not too difficult to learn. So we'll use that one. We also use only 2 classes here. If you want to include all 10 classes, you can uncomment that line. If you want to have even more classes, you can use extended MNIST there. So that's part. And now we go to the code where we need to change some things. So if we go inside the phased LSTM cell, it's right now just a vanilla LSTM cell. It doesn't have yet all of the things that we need. So a couple of things that we need to do is first to add some parameters. So for LSTM, it's just a hidden size. Maybe you can add also dropouts. I have seen dropouts inside LSTM. That's quite common. So one thing is the alpha. Alpha will be that leaky parameter that will allow the gradient to flow even if the gates are closed. That's only for the training, not for the test, for the inference. So alpha would be maybe even, I don't like to write it like that, e minus 3. Yes, e minus 3. So yeah, in the paper it's written 0.01. So anyway, so then in the paper they also have very interesting way how they select the initial tau values. If you look at different tasks, there is written, maybe I can show you just a second. So that alpha parameter we need, and we need also the tau. So tau, if you look at these lines, they say that, I'm not sure if this one was the line, but they are here, right? The period tau was drawn uniformly from exponential domain, and they compared different kind of domains. So it's like exponent function from uniform distribution drawn from 0 to 2, or 2 from 2 to 4, and so on. So they have quite an interesting way of initializing the tau values. as you know, like for the LSTMs, the initialization part is quite important. It kind of like makes it work good or bad. I'm not sure like which kind of initialization would work best for this particular task, but we'll use one that was referenced in the paper from 0 to 3. So tau max will be 3.0. Then the R factor, R on, as in the paper, that was 0. So we can again write it 5e minus 2. Okay, so we have these. Let's see why it's okay. Yeah, cool. So we have these three then. These three, right? Those three parameters. Okay. Then the learnable things. So we will add, of course, you can learn more of those things. You can learn all of them, including alpha and R. But we'll learn only tau and S or shift. So self tau. Tau parameter will be torch nn parameter torch float tensor. And here's the interesting thing. One like I think it's not specifically mentioned in the paper, but it should be the size of the hidden size, because there were the Hammond product. Probably that's, if they would use just a scalar value, they would not use the Hammond product there or the pairwise calculation. That's why it's probably the size of hidden size. So just the one thing is, yeah, hidden size. Let me check. Also, I'm a little bit yeah, it should be like that. That should be fine. Hidden size, and then the initialization from uniform from 0 to tau max. So in PyTorch, if there is this underscore at the end, that means that you execute the that kind of distribution sampling for the vector that you choose. If you use without that sign, it will, I think, return the distribution itself, not actually the drawn samples. So, and then at the end also the exponential function, like that. That's also interesting. Should I use the sign? So yeah, we can use it like that. So self shift. So we call S as shift, so it's a little bit clearer that the idea is for the shift, and the tau is like time interval. So I mean the frequency. Torch and n phased. So frequency and shift, I think that was those two things. Parameter. Torch float tensor, right? Again, the hidden size. And again, in the paper, they write that the initialization for this is based on the tau. So it's again from uniform from 0 till the value of the tau. One way would be that you could draw uniform for each of the dimensions of hidden size by the selection of the tau. But the uniform function, as I think, works only with scalars. So we could try to use torch mean, maybe mean or max self tau, just the value of that, and item will make it as just a floating point number. And so that would be approximately what they had in the paper, hopefully. So tau and shift like that. What I could do? So if somebody is not following all of these things, maybe I will add a couple of small screenshots in the chat. Meanwhile, while I'm coding this, so if somebody wants to follow this, and I'm doing this too fast, just a second, trying to make a screenshot link. So I have the screenshot link. I am copying that in the chat. So this part of the code, and also the initialization part of the code here. So I will drop those in the chat. And then we'll need to just implement the forward pass. That is the most difficult part. So yeah. Okay. So I dropped in the chat those initialization parts. So then here we can maybe in between the for loop and the sequence of permutation, we can calculate the phi values. As phi is based on the tau and shift only changes when you learn them, when you have the backprop and the weight change. So we can calculate all of them directly for all of the states before the for loop. So we don't need to calculate on the every for loop. So to do that, we first need the vector or matrices of the time steps, so time step indexes. So we can write times torch range. So this particular task is very nice because all of the sequence lengths are the same. For the language modeling tasks and some other tasks, it will not be that fun. So that will be really not fun. So size 0. That is the batch size. No, not the batch size, but the sequence size. Sorry. So maybe I can even write it out so it would be more clear. Sequence length. So this is that one, like that. So just for clarification. And then we unsqueeze dimension of 1 because we want that these times vectors would be the shape of the hidden size. So now we would have the sequence by 1, but we want this to be sequenced by hidden size, so we can use some of the functions that we already know how to use. One is either the repeat function or the expand function. The expand function just copies the pointers, and the repeat function actually copies the values. So before we use the repeat, I think we also could use the expand in those cases because it's not really important to copy them, I think. So in some cases you cannot copy them, so cannot copy pointers. So here this will be the sequence length, comma, self hidden size. So just preparing the vector, let's say matrices of those indexes. Then one thing that's necessary is to move this matrices to device where we calculate all of our function graph. That is probably later on GPU. For the testing purposes, this will be CPU. For when moving that to the Google Colab for the testing, then we'll use the GPU. So this line. Then we can calculate the phi. So phi, that was in the equation. So let me show the equation. That equation was with the mod. So where is it? So here, this part with the phi with the mod. So we'll calculate that one in one go for all of the sequence. So we'll go back to the code. So the phi here, f mod. So I provided with this nice function that good people from PyTorch forum provided us. So we can use that one. So if somebody knows how to do how the TensorFlow derivatives for fmod works, then that would be great if somebody can explain me. I didn't have time to explore, but this is kind of interesting because how they derive the gradients for that. So self tau. So this is one is times minus shift, and then the modulus of tau, and then it's divided by self tau plus I would like to add some epsilon to avoid division by 0. So that is like that. Then the alpha is self alpha, but in the case of if not self-training, so the one thing I will write it down as well, why it's not here, training, it should be, it is inherited from the torch-NN module. Alpha should be 0 when it's in the inference phase, and you can get model in the inference phase. As you know, it's down in this code lower part. It's written like this, model eval. So it just makes this flag training to false, and this is mainly used because in models they have dropouts, right? Dropouts. If you don't make Monte Carlo some kind of what was it called? This was some kind of Bayes Monte Carlo networks or something like that, where you leave dropouts on even if it's in the inference mode. Then of course you would not use it, but in most cases you switch off the dropouts so you can have consistent results. You will not get unexpected results in production later when something drops out in your model. So we'll use this one. Then the k-gates. So the k-gates is this three-part equation, this set of three conditions. So we can use the k torch var, torch var. So the first part of the equation is phi is lower than 0.5. Actually, I also did not investigate how often each part of these fire. That could be really interesting to log the actual like how many times each of those gates open or not, like the equation, these conditions are true. So that would indicate if the R value is correct or not, because the R value controls how often all of these gates open. So, okay, we'll write this one. And in case, if this is true, then we get 2 times, so that is the right side of the, in the publication, they had the right side of that equation. So 2 times 3 divided by self R on. So R on will not be 0, that's why we don't need to have the epsilon. Then the other part, again, torch var, we'll split it again into two parts. And here it's a little bit tricky, because in a Python, of course, you can write, in a simple Python, you can write 0.5 something x, like 1.5 or whatever. And this would be the normal syntax for if statements of comparing scalar value in range. In Torch, working with vectors, it will not work like that. So that's why we'll use the Torch logical and. Interesting that the autocomplete thinks that there is no logical and, but there is. So one is 0.5, one boundary will be 0.5 R on. So this will be one boundary, so with a phi, and then the phi on the other side will be self R on, like that, right? And then the then there will be these two parts of the output. So one will be 2 minus 2 multiplied by phi divided by self R Self are on. Okay, like that, right? And the other one will be this leaky output, leaky gate, basically. So it's a little bit open gate. So alpha phi. Hopefully this part will be okay. If not, then we'll fix it later. But I will again add the screenshot of this part of the code so you can catch up, because probably this was too fast. So I will maybe also leave this open for a moment. Hopefully there is no errors. Okay, the next screenshot link is also in the chat. Okay, I will look at this a little bit, think about it. Actually, we have very little to change to make it workable. So we'll wait for you to catch up. So yeah, maybe I will write in chat. So are you ready to move on? So plus minus working on it. So at least one person says plus. Let's see about others. Okay, 2 pluses, just a second. I will make sure. I think I ran in Google Colab some experiment that I wanted to compare the results, but fortunately seems like I run the... Oh no, there is a phased LSTM. Oh, that's cool. So this is a phased. So hopefully I will have something to show you by the end of this tutorial. Hopefully some good results, not bad ones. It's just training very slowly, even in the Google Colab. That's why I'm just checking. So, okay, I have 2 pluses, not sure about others. Should I wait? Should I wait or move on? Let's see. Okay, another plus. So I assume that I can slowly move on because there is not that much actually left. So one is then the sequence, of course. So here we need somehow to select from the K the correct time step. That is very easy because in the PyTorch all of the tensors can be enumeratable. So you can get the indexes here just like it would be simple Python list. So the PyTorch is very Pythonic, basically. Like the TensorFlow a little bit different. So here we can enumerate that one, get the T here. That will be this part, and then only we need to change these 2 lines at the end by introducing new gates inside our system. So we can introduce new gates in our system. I will also later check what hyperparameters did I choose. So anyway, these will be so the C, what we had C before, it's actually will not be C anymore. So this is going to be the C prim now. So C prim with that tilde sign on the, I'm not sure, like if somebody knows how how it's spelled correctly in mathematician language, then please tell me. So C prim here, it's not actually C hat as well because there's like tilde sign. So C prim there and also C prim here, and this is also H prim. So these two lines will look like that. And also, so maybe I will, let's look at the equations once more and then we'll implement them. So the equation, where are you? Here, the 7, 8, 9, 10. The 7 and 9 is the same as in vanilla, and then 8 and 10 are new ones. Looks a little bit similar like binary cross entropy type of thing, but basically it's like the gates, one side when you open gate, the other side it closes, and the opposite is also true. So kind of interesting equation. So if I go back to the code, so this line will be then the C. So it's nice that this code is basically what we wrote last time, so we can you can imagine that all of the stuff you wrote from scratch basically. So K, T here, and then the C prim. This is a first gate part, and then the second part of the gate is K, T by C multiplied by C. So these are the pairwise multiplications or Hammond products. And here, I think we can just copy the same line from C and just change this to H. I think it was like that. If I'm mistaken, then correct me. Like that. So the H prim, yeah, H prim, so cool. That's about it. So I think we're kind of ready to launch. I will add these equations also to the screenshot. Copying, adding to the chat. Yes, copied, adding to the chat. Cool. So this I have. Okay, I added the screenshot to the chat. I don't want to scroll it immediately away. That's why I'm trying to look up in some other way just to see what kind of hyperparameters I gave you, because now in the very beginning we'll have 28 input features. Okay, so that's a good point to test. So if I run this code, let's see if it works. Maybe we have some bug, maybe we need to change it a little bit. Usually I have bugs. It will be very surprising it will be without bugs. So it works. It seems like, okay, yes, it has bugs as always. So debug with an alpha. So yeah, so I was thinking that I added the self alpha and self are on to the constructor, but I did not do this. So if I go back here in the constructor, I gave these parameters in, but as you see they are gray and they are not stored anywhere. So let's store them by the hidden size. So here the alpha and self are on, because we need them in the forward pass, not in the construction part. So I also will give you a screenshot of these small changes, just those two lines. And we'll see if it works now. Now we're testing with 28 dimension length, the input size dimension. So this will be 28 input features with 28 sequences, sequence time steps. That will be a very easy task. The vanilla can also learn this, but the more difficult task will be if we make it with, let's say, 1 or 2 input features. That immediately will increase the, so it works for me. So for 200 samples, just to remind you that I also give you the image right now. Don't forget that in chat that you need to change these lines. But if you go up here, you see that if the CUDA is not available, then we cut our dataset only to 200 samples. That's why it works for me on the CPU. But here, the actual complexity comes in. So let us think. So if it's 784, so if we would set the input features to 1, then the sequence would be 784, and it will take a long time to run. But we can also try 2, and that would create then 350, 392, 392, hopefully, that I calculated that correctly. Yes, so, and then, so that would be like, so the sequence, like, then basically this would be. And also, I think we should increase a little bit the, so let's say we can add this to either 1 or 2, so I will use 1 in this case, and here we can add more classes, 2, 3, 4. Also, you could add even all of them, but that will be very long to train. So, and then you can copy all of this code and put it in the Google Colab, and we'll see what we have there. So in Google Colab, my Phased-LSTM is already running for some time. I even started running it before we started this session, and it's still only in the second epoch. So it takes a lot of time to run, but of course we are not after the speed, but we are after the accuracy and the abilities of these Phased-LSTM models that are able to cover very long sequences. So here I have with these nice cats and dogs running around the Google Colab. In this Google Colab, I'm running here the Phased-LSTM. Where is the phased? So, okay, so hopefully I did not stop it accidentally. So Phased-LSTM. Here I have Phased-LSTM, except this is not Phased-LSTM. So fail, I think this will be a fail for me now, because I thought I run the Phased-LSTM. So anyways, here I have after the so this is, I think this is like the simple LSTM. So after the second epoch I get 83% of accuracy on the test set. And the expectation is if I run the same model with Phased-LSTM, I would get better results, faster. And I actually did these kind of experiments before. Maybe I can find some of the results. You can try this running yourself, of course. You can try to applying these things to some more serious tasks. But so before I tried to run this thing with very simple tasks. So where is it? Okay, it's not opening. So now this is a very long sequence, but before I think I ran it with the input size of 2 or 4 or something like that, and then I got that in the second epoch I already with Phased-LSTM I got 100% accuracy. So and then with the simple LSTM in the second one I got 97% accuracy. So it is faster and better, but it especially should be faster and better if you have very long sequences. And of course, you need a little bit to fine-tune the hyperparameters of the R and also the alpha. But R is the most important one, and also you can make R learnable, so that is also not a problem. Okay, so yeah. So I think that's about it for today. I hope that you got your code running. I hope that it's interesting and valuable for you. So if you have so many questions or something, you can write me.
Thank you. Yes, very interesting.
Cool. Happy to help. So and next time we'll meet with again with the small template, and I will try to show you the some of the very interesting hacks that you can use for improving LSTMs. So I found one blog site where they listed all of those hacks, and when we tried that on our models, we definitely see a huge improvement. So and actually, if you read in the PyTorch blog, forum, they are debating of implementing some of them as default ones. For example, the layer norm LSTM. So that is definitely helping, and this should be basically your default LSTM. So that's about it today. So we'll meet next week. So thank you.
Thank you.